Lithuania. Okay, already for a long time, since early days, humans have been interested in figuring out how we can interpret the universe. That is one of the goals of physics, is figuring out how things work. But it's also an inherent thing in all of us as human beings. One important way in which we understand the universe is by understanding through our senses. And a very important sense, of course, is the sense of sight. And even with the early Greeks, they were interested in trying to figure out how we see and what is the nature of light. One of the ideas that they came up with, a general concept that they more or less agree with, that light in straight lines is exemplified in this picture here. That's not a picture of ancient Greece. And therefore, with straight lines, it looks probably. They also had the idea that light is particles. Now, coming back to that, they called them atoms of fire. Similar to some of the Greek philosophers' ideas about the nature of material being composed of the most indivisible type elements, and they called them atoms. Even since 700 AD, also the Greeks, and I use the word loosely as the humanists and historians would know in the crowd, that includes Assyrians, Babylonians, Egyptians, and other peoples from the Mediterranean. This is a lens that was found in Nimrud in Assyria, and it's in the British Museum. It's from 700 BC. It's not a cast lens, it's a polished lens of quartz. So obviously there's some sort of refraction, and they also wrote about refraction. Reflection, a very famous case of that. The story goes that Archimedes was able to set fire to the Roman fleet in the harbor of Syracuse when the Romans went to invade Sicily at Syracuse. I'm not quite ready for that one, but I'll go ahead. And one thing I will point out is that even though the Mythbusters said they couldn't get it done, but they just didn't do the experiment properly, they didn't disprove it, in fact, because MIT went and did the experiment themselves just a few years ago, with a very successful setting a Coke boat on fire. The other thing they had was a very interesting theory. It's called the emission theory of light. I don't know if you've heard it before. When I first read about it, I was slightly surprised. It's the idea that we see by light coming out of our eyes and illuminating the object we're viewing, and that's how we see the object. Now, of course, some of us might be laughing about this. How they figure out that. Well, it turns out in 2002, there was a study done at a university with the psychology department. It's a published study where they found about 50% of the undergraduate students at the university believed in the emission theory for light. That wasn't done at all. So that's the ancient Greeks. But just so we're not Eurocentric or Mediterranean-centric, this idea of studying our ability to visualize the universe is universal. So the Chinese, under the leadership of, well, he wasn't the leader of China, but he was the leader of the philosophical method, was Mo Zhu and his followers, Moists, were actually big in science in China. And besides a lot of philosophy about culture and politics, he also did a lot of work on science itself, and had the idea that light is also moving in straight lines, that there was refraction, reflection. Also the camera obscura, which is also known as the pinhole camera, they had developed already in China. And then around 1000 AD, Al-Hassan, born in Basra, Iraq, moved to Cairo. He got very famous because he had told the dictator of Egypt that he would be able to control the flooding of the Nile, which of course is quite a drastic occurrence every year. And when he went up to go try to build the dam at Aswan, he realized this is a project way beyond his abilities. And so he feigned insanity so he wouldn't be executed. And he decided to change his profession and decided to do science. So it's a good thing for us. He wrote a book on optics. He was the first one to write down the description and do experiments with prisms that dispersed white light into many colors. He also did the camera obscura and developed an optical model for the eye and did many experiments to disprove the theory of seeing by emission. Okay. So we're going to jump ahead. We're going to the 17th century. There's a great video by dailymotions.com to search history of light waves and photons. In the 17th century, there are these two different philosophies come forward to describe what is light. One of them is proposed by Newton. Newton was a fantastic scientist for lots of different reasons, which I won't go into right now, but one of the things that he did a lot of contributions on was the study of light. His idea was that light was composed of corpuscles, similar to what the Greeks had the idea of particles. He was also able to do lots of experiments, and one of the experiments he was able to do was to show that white light is not only composed of these colors, that you can break it up into many colors, but those many colors can be recombined to make white light. So people before had thought that perhaps there was something special happening in a prism which created these different colors, but that white light itself was a pure light, that it was not a combination of different colors of light. But he showed that that was not the case. In fact, he showed white light as a combination of all colors. On the other hand, we get Tristan Huygens from Holland, I believe. These two were fierce rivals, and it actually got personal. And Tristan Huygens believed in the wave theory of light, which was supported by the idea of using, for instance, explaining a phenomenon called diffraction, which I'll talk about later on, which demonstrated some kind of wave-like nature for light. But these two are in big conflict. The philosophies are in conflict, and I don't know why that one's green and that one's red. Light comes in many colors. The interesting thing is that science is one of those fields that has an advantage that we can test the results, but sometimes people who speak loudest win the day for some time. So for some years, Newton's idea that it was corpuscles rather than waves held the day, until we get to James Clerk Maxwell. So in the latter half of the 19th century, James Clerk Maxwell, a Scotsman, really great physicist. He did one of the fantastic things in physics. He was able to combine together the two different fields or forces, the idea of electricity and magnetism, into one complete theory in his four Maxwell's equations. I won't explain them, but for the physicists, they love seeing that. That's a really nice equation. But the interesting thing was, though, not only did these four equations describe how does electricity and magnetism represent two faces of the same thing, he also was able to take those equations, manipulate them, and come up with an equation for a wave. And this equation for a wave depends upon a magnetic and electric field oscillating perpendicular to the direction of travel. So if the wave is moving from left to right, as I indicated the arrow, the electric field would oscillate vertically, for instance, and the magnetic field would oscillate horizontally. What's interesting, and kind of a little caveat, just to show we're humans as well, when we're physicists, and that is that when he did this, he was engaged to a lovely Scottish woman, and he took her for a walk in the garden, and it wasn't raining, so it was a beautiful night in Scotland. And she had noticed the stars shining and said, "Oh, isn't this romantic? And the starlight is beautiful." And he goes, "You're speaking to the only man in the world who actually understands what it is." So he had a bit of an ego, but he was correct. It is the other thing, the take-home message is not only is light an electromagnetic wave, according to Maxwell's equations, also what falls out of this equation is a calculation for the velocity of the light, and that depends on being just physical constants. The constants gives you a velocity of 300,000 kilometers a second, and physicists perversely label this c. And so you have to remember c is velocity of light. Now the interesting thing with waves is they have a wave length. Just like ocean waves have a length, right? The distance between one crest and the next. Light has exactly the same kind of thing. Of course, they're different physical phenomena, but they're both waves. And different waves have different lengths. They have different lengths. We've heard of gamma rays, X-rays, ultraviolet light, visible light, infrared, microwaves, radio waves, all long radio waves, short waves, all these kind of different waves. They're all the same thing. They're all electromagnetic waves. The only thing that distinguishes them is their wavelength. Why do we distinguish them? Is because the interaction with material depends on the wavelength, which also tells us what the energy is in the wave. So different wavelength ranges interact differently with materials, and therefore we've given them different names. But they're all identically the same thing. They're all electromagnetic waves, only different in wavelength. I've highlighted here, don't look at that one, please. the visible portion of the spectrum. It occupies a very narrow range in a huge range of wavelengths. By the way, this is a logarithm plot here. So it goes about 25, 28 orders of magnitude. If I wanted to do this properly, I'd have to go from here to Raleigh to stretch it out so you can see all the different numbers. The other take-home message is that we have short waves like gamma rays, X-rays, they're high energy. When you have radio waves, long waves, they're low energy. And that our visible light that we see is in this very, very narrow band of waves. Red is around 700 nanometers, that's 700 millions of a meter, and then, billions of a meter, and 400 nanometers blue violet. So we can go into nature and observe the wave-like characteristic of light. One of those is the idea of diffraction. Diffraction depends upon the wavelength of the light and the physical structures that the light is passing through. If you want to talk to me afterwards about all this stuff, you can in more detail. But you can view the phenomenon yourself, for instance, with a peacock. You can't do it by looking at the peacock here, but if you go see a peacock in real life, some of the colors in the feathers of a peacock are caused by diffraction. And with two of our eyes, because the diffraction depends on the angle that we view it, we have a slightly different color in the same part of the feather. And this leads to what's called iridescence in peacock feathers. So go look at a peacock sometime. You can also observe it with a DVD. It's pretty easy. You can see the different colors in the DVD when I do this. You're supposed to say yes. Then you can also demonstrate diffraction by using a DVD. It's got lots of very fine structural lines in it, and they diffract the light. And you see different colors depending on the angle at which you view the light. So that's a clear demonstration of diffraction, and that's also a characteristic of a wave nature for light. Another one is interference. Everyone played with soap bubbles as a child. Again, look at color on the left. Your left, my right. The interference of light depends upon the thickness of the film that the light goes through, reflects off of. The two waves can interfere. It depends on the wavelength of the light and the thickness of the film. As the film varies in thickness, you'll get different colors interfering differently. And that's why when you have a soap bubble, you look at it as a child, you wait a little while, by gravity it gets fatter at the bottom, so it's thicker at the bottom, thinner at the top, and you're changing colors within that soap bubble. Another application of that is for photography or for microscopes, is they put multi-coated layers on these so we can actually interfere to remove reflection. Another thing is polarization. Polarization occurs because, remember, the light wave is an electric field which is oscillating perpendicular to the direction of traffic. So we can polarize the light to be like this or to be like that. When we do this, and you guys, I know everyone here has already observed this phenomenon. If you wear Polaroid sunglasses when you're driving, you get rid of reflected glare. That reflected glare is polarized, and so you're using the sunglasses to block a particular polarization state of the light. You can do this for fun if you go into a store like Polaroid sunglasses. You get one pair, get another pair. If they're polarizers, all you have to do is turn one 90 degrees with respect to it, and it'll become black. I'll demonstrate that now. So here's one polarizer, and here's the other polarizer. They're aligned, so you can see through both. When it turns through 90 degrees, it gets black. You use exactly the same thing in the store, really annoy the light is produced how? And there are basically two different ways we can understand the emission of light. One is called incandescence. So an incandescent light bulb produces light by heating up the filament. When it reaches a high enough temperature, it starts to emit light which is visible. If it's a cooler temperature, it emits light that is longer wavelength, lower energy, like infrared, etc. So here's an example of that. We have 3 different light bulbs at 3 different temperatures: 2,700 degrees Kelvin, 3,500 degrees Kelvin, 5,500 degrees Kelvin. The hotter light bulb, maybe this is a better picture. The hotter light bulb is a more blue color, and the cooler light bulb is a more red color. When we have cool objects, they radiate with longer wavelengths, more like red light. Hot objects radiate light with shorter wavelengths, more like blue light. So it happens in astronomy. You look at Orion, there are 2 different supergiants in Orion. One is blue, one is red. And they just have different temperatures. You can also see this outside of the visible range. So for instance, here's someone holding a plastic bag over their arm, and that's just a reflected light image. And again, it's horrible. Look at this one, looks more alive over there. And then we took a picture with an infrared camera that's sensitive to infrared light. And what you're seeing in the bottom is the light emitted from the person. You can't see it with your naked eye because it's in the infrared range. It's not hot enough. Luckily, if it's 2,200 degrees Kelvin, he's dead. Around 300 and change Kelvin, so he's alive. And he's emitted infrared radiation. You'll notice that the infrared radiation passes through the plastic bag, for instance, around his hands. That doesn't pass through his glasses, though. They're black. I'll come to that in a moment. It turns out there's another way we can understand how light interacts with material. One is the emission of light and one is the absorption of light. This is done in a quantized way. This can be at best explained by Max Planck and Einstein and Bohr. The idea is that Colin will expound on this, that atoms have electrons in them and they can reach different states in which they have more energy or less energy. When they want to go from one state to the other, they need to emit or absorb energy, and they do that in the form of a light photon, a light with a different wavelength depending upon the energy. For instance, if you look down here, you're seeing the top three spectra, emission spectra. So if you take a lamp, like a mercury vapor lamp, that's the middle one, you'll see different characteristic wavelengths that correspond to different colors. The different colors correspond to the wavelength. In the bottom, what you see is an absorption spectrum. So light is being absorbed with the black lines in the spectrum, and it depends upon the material that's doing the absorption of the emission, which kinds of colors you get appearing. Absorption of light also occurs when you look at stained glass. Don't look at the screen. Visible glass, visible light passes through, but it blocks infrared and it blocks right off with UV. If you want to get red glass, if you have red glass, it's going to absorb the other colors except for red, and that's why it looks like that. And if you want to look at art, you can use visible light. That's the middle picture. Don't go here. Middle picture. On the left-hand side is reflected infrared light, so you can use that to probe how it looks different. And if you look in detail, there's contrast changes depending upon if it's infrared or visible light. It depends upon the material, the absorption of the light. And then you can also try to get light to, you can get material to emit light. And here we're using ultraviolet light to get some fluorescence on some of the face of the queen over here. Finally, what I want to talk about is how do we proceed. Color vision is terribly important. If you're going to be an artist, you want to understand how to do that. We only have 3 different types of receptors for color in our eyes. One which is sensitive to the short wavelength, one which is sensitive to the middle wavelength, and one which is sensitive to the long wavelength, or to the more blue region, the more green region, and the more red region. We only sense with those 3 different receptors. How do we perceive all the other types of colors is by a combination of the stimulation of those different receptors by different amounts. So for instance, yellow light would stimulate the long and the medium, but not the short one, so you would not see the blue. You would interpret that as being yellow. If you had something which was cyan, it would stimulate the blue and the green receptor, but not so much the red one. Even though you don't have a single receptor for cyan, you do have one entrance. And to demonstrate that, I have a light box here. You see red, you see green, you see blue. When I put them together, magenta, cyan, yellow, and white. So white light, as Newton did in his experiment, is a combination of different colors. And in our case, it's a combination of the 3 colors that we need in order to stimulate our perception of light. And with that, I think I'll turn over the discussion to Elizabeth, who will talk about how we can understand this in light of art and how we need to deal with art.
So what I'm going to walk you through are various aspects of the material processes that I use just when I'm producing my artwork. This isn't a grand statement about all art, it's just a focus on what's in front of me most of the time on the table. And so when I sit down to make a piece, the way my process works is I begin by writing. I often start with a word or a question, and then I get into the flow and analyzing. I reach for the materials I've brought to my studio table, or I'll take the feeling and I'll sit with it and I'll wrestle with it. And I just like, it's really an intuitive process. I feel it moving around. I try to get a sense of what colors the Stephen might have, or a texture, and not in a literal way. I really try to get out of anything literal. And I play with the materials around me, wondering what would happen if I dot. Or I'll put on some music and see if the song can help me click into that feeling or that idea. And then I'll do everything I can to stay in that state of flow. And what I do is I cultivate the vibe so I don't have to think. I'm trying to turn off my thinking so I can be entirely intuitive in the process. And then I go back and analyze it later. And when I sit down at my table and I begin to work, I'm not thinking about the nature of my materials or the process that I'm going to be using to connect with things. I'm aware that the materials that I choose are the voices of my piece, and I'm thinking about that and about my narrative, and that's where I begin. That said, I do have a deep concern for and a relationship with my materials because they are the undertone or the subtext of what the piece is going to convey. So I make my own paper, and I try whenever I may to use it. Every summer I go up to Stevens Point, Wisconsin, and work with the same group of friends. We've been doing this for about 6 years now. And we make enough paper for everyone for the whole year. So there are about 4 or 5 of us who can pull sheets. It's very, very physical labor, even where every muscle in your fit is. And the handmade paper process can be broken down into 5 simple actions. So if you think about it as a treating fibers process, what you're doing is you're beating them, you form the sheet, and I'll show you a little video of this. You post and press the papers, then you stack them, and then you dry them. And what you're doing is you're macerating the fibers till they're open to becoming hydrated. And they become receptive to and saturated with the water, and usually we put our pigments in the vat after they've been macerated. You can't put them in, and this is a Hollander beater. So if you imagine under that silver part, there's a giant water wheel of blades that pound the fibers. They don't cut them. This is the difference between, like, in my opinion, the handmade paper I like to work with and the sort of lower key version where you're using garbage disposal. That cuts the fibers up. It opens them in a very different way. So it's a different kind of receptivity. Okay. And then this is iris. So a friend of ours just cut all his irises down, saved all the leaves, dried them out, and we're mixing this with another fiber to make paper. And for me, one of the things is, and the reasons why I like to use handmade paper is because it's like skin. Paper, like skin, has a memory. It takes scars. You can get rid of them somewhat, but they're always sort of part of the memory of the piece. And I think that feeds into the narrative. Even if it's a subtext, even if you don't know, the memory is there. So we work with these are just some of the fibers that we work with. And up top is abaca. So when I buy abaca fiber, which is, it's a Philippine word for manila hemp, and it's from a stalk of a banana tree. And then on the bottom, that's kudzu that I harvested down on Holly Street. And I got there, it was all moldy. So we had to strip it out and dry it, but it's just the stems. And then we strip out the stems. And when I was making that, and then I'll get to this, my goal was partially to make a southern paper, so it was made out of cotton and kudzu. But I'm also looking for renewable resources, partially because we use so much water in the process, and partially because all materials are finite. Kudzu is pretty plentiful, and I hope to use it more in the future. It makes a really beautiful sort of tannish, greenish paper. So when we're making our paper, we have a lot of objectives, and these are some of the things we can have. The soda ash is for boiling, like if I set up a bin of black walnut husks, which you'll see in the set, we have to use this to neutralize the acid. That's just the natural flavor. And the reason why is I don't want my paper to eat itself. Yes, it will take a long time. No, we may or may not see it in our lifetime. But I really like the idea of cannibalistic paper, not appealing to me for my artwork. And these are just common things you add. Sizing controls the shape and the page and the quality of the writing surface. What's in this lovely picture is formation aid. It's like house fit. It's really disgusting. You're like okra glue, similar derivatives. But what it lets me do is make a super, super thin sheet of paper. And so I've come to love the powder. And then these pigments, I'll show you a picture of that set, and then retention aid, which helps the fiber hold the paper. I don't like fused pigments. I want my book to stay the same color it is the paper. So just on the left are the pigments, on the right are the walnut husks. Water for me is a really important resource. This process would be nearly impossible without water. So it also, my concern for the environment and the longevity of my piece it's a global concern. Art making is a global process, even though when I'm making my paper, I'm thinking about building a perfect sheet. But what I've never thought about until I talked to Suzanne was what's in the water. I drink it, I don't think a whole lot about what's in it unless it's muddy or rusty or unless where my hair turns red because there's so much rust in the pipes. This would affect it, but in Wisconsin the water's pretty good. It doesn't cross my mind to think about it until now. And so my body also informs my work. The fact that I would think about how that material interacts is as important as this material. This is making a sheet of paper. This is the part where it's forming a sheet. So we've beaten the fibers, we mix them with water, they're in the vat, and that's called a molding decal. So when you buy paper with a deckled edge, it's talking about that frame. And the fibers, some of them will, you hold the paper, but some fibers get under. So it'll have a softer edge. So that's a deckled edge. And this is the decal, it comes off. You have to drain all the water out. And underneath there, she's got hand woven mold, so it's brass wire that's been woven. And that's what gives you the pattern in the paper. When you hold it up to the light, you see watermarks and lines and chains. That's what's going on. So we do this a couple hundred times a day, and then we go relax. Friends come from all over to do this. This summer we're doing this friend, the Nestle recommends. Coming in from London, a friend who doesn't even make paper comes every year from Chicago because she likes to look in it and hang out. And that's called pushing the sheet. And what happens is it's the water tension that holds it to the mold, so we're transferring the tension onto the industrial felts. And that's the cut of paper. So it's pretty close to that color when you're done. Then we stack them up, all the felts get stacked up, they go to hydraulic jack, and all the water gets squeezed out. That's after the water's done. We pull them out, we make sandwiches of blotters and corrugated cardboard. So then the next morning we unpack the entire post and restack them, make new sandwiches. So it's a two-step drying process, and then they sit for a couple days under pressure so that the sheets remain flat and you don't get cockled. And another thing we do is sometimes we put inclusions in the paper. You've all seen that paper with marigold petals in it, which is not good for your printing type. Or it breaks type. I printed one wedding invitation and I was done. No, I won't do it again. And then the piece on the right, I don't know, you can kind of see it actually more on this side. The little fibers there are raffia. You know, you buy a gift and it's tied up with raffia. It makes beautiful paper, and it really adds something that's narrative that wouldn't normally be there. But you can put anything in paper. And then when I do formal bookbinding, the hardcover book, we use what's called Davy board. This is a new exciting discovery. It's a symbol for acid-free, which in all these years I've never seen on a single thing I've bought. It's online. And I just put the text in there. So these are all things that you would look at. You get these massive descriptions when you're looking for things to buy. The idea is that it's got a neutral or basic pH, but it could be made from any cellulose fiber as long as the active acid pulp is eliminated. So, it's just a question of processing. And when I'm thinking my journals, I'm using Davy board. The irony, which my students have also had the pleasure of learning, is that although it's supposed to be archival and acid-free, when you cut in, you can cut a little window in so that you have a dip in it and you can, put a picture in there or something. I found broken glass in my Davy board. I found metal in my Davy board. If I'm cutting my Davy board and my X-Acto breaks, I have no way of getting that tip out. And now I'm starting to think, what does this mean long term? Because does it rust? What's next? It's a little unnerving, and I'm going to block it when I make it. It's going to be something beautiful. Ink, all ink is pigment and vehicle. It doesn't matter what medium you're in. There's a pigment and there's a way to get it to where you want it to be. All of these variables are negotiable too, which is kind of nice. The pigment imparts gloss, color, and texture, the other characteristics to the printed image, and they can be black or white or any color. And the ink vehicles, the fluid are the ink that transports the pigment onto the substrate, whether it's paper or canvas. Pretty much anything you can think of. Wood, that's a good place to start. So all I did is I sat down when I was putting this together, like, okay, what kinds of things can I use to make a mark? What really common assignment when you're starting out in foundations classes, what can you use to make a mark? Make 40 marks. You think 40 marks, oh my God, there's no way. And then you just start listing them, and this is the history of humanity. It's part of our basic composition, like when you go to the beach, everybody digs holes, which you don't understand. It's our natural inclination to make a mark. So these are just a couple of things off the top of my head. And you've probably done all of them without even thinking about it, except maybe the actions. And hopefully you'll come to that pretty early. But to think about the way that a conservator might approach these materials, it does change your process and the way you think about things. These are linoleum cuts. All of you guys, or a lot of people do lino carving in school. In 4th grade usually, you unicorns, snails, your name, which always reads the wrong way. But what I started thinking about is every time I do this, what if this, now it's truly changed my thinking. What goes onto the paper? How much of this transfers onto the paper? Every time I use a new blade, whether it's a carving tool or an X-Acto, the blades are oily. And I know it because every time I cut myself, I get an infection unless I clean it out right away. Everybody who uses them. So what is this material and what's happening to it? Again, for me, it's a body informative process. I know because I had that infection that this wasn't clean. And I'm not really going to clean my blades, sterilize them or something just to use them. They work perfectly well. I can get as detailed as I want to. But then, what is my responsibility? Now I'm starting to question what's happening here. So the same applies for hot type, hot metal type. Some of you guys are press printers. This is an old printing machine, or excuse me, a type foundry machine called a monotype. And each of these lines this is each a line of type, but it's not connected. Each one of those is a little metal piece. And I'll probably scroll forward. What's happening is there's a man who sat down with a keyboard, and on the keyboard there's a drum that's got all these mathematical calculations. And you type each line. So if you imagine just one sentence that I just said to you, you've keyed in the whole thing, but you've also keyed in the spaces in between the words. You've keyed in the spaces at the end of the line so that everything has a perfect margin. You've had to figure out how much extra space you're going to need just so that the entire text is even. And it's all like pistons and really great, it's hot lead, very sexy machine, and I love these machines. But the sound, if you magnify this by about 50 times, that's what it's like to be in a shop. And I feel like I'm married to this already. Those little knobs, it's 1,000th of an inch. And so what happens is you've keyed in, that's the paper roll. So you've keyed it in, it works like a player piano, and down below there's a matrix. It's a square thing. It's like almost like a spatula, or a type mold. And that's telling the mold how to move around. And then it shoots the metal into each letter that gets, turned around, and then you see it come out the bottom. So it's the mind that would conceive this is enough to get you want to do it. And this is how all newspapers used to get printed. Broadsheets tended to be wood type, but even still, we have a person in our department, Ted Longworth, and Jonathan designer type, who are making wood type again. But that's a matrix. So you see it moving around, bringing the punches on the player to the keyboard. And then So when you use type, this is type that's been set. That's totally new type. It's always really shiny and exciting. And this is just regular type. So the one on the right, when you print, you can use a combination of both. And then so now I'm thinking, okay, so what's that doing with the paper? You know, and then putting ink on top of it, which is getting punched through the fibers. There's more to think about when I'm ready to think about when I'm thinking. It's very interesting. A couple anomalies. Walnut dye that I showed you cooking before, and oak ball were common inks from the past. And one of the things they're finding now, and I've actually seen some pieces like this in person, it's exquisite. The type is rusting away. It's removing itself from the paper, which sounds really cool, and you want to figure out how to do it until you realize that it's becoming completely destroyed. This information will be lost over time. And the gall is really disgusting, actually. It's a wasp who oviposits its eggs into a leaf bud, and then they grow into those little balls, but it's really terrific. And usually there's something like gum arabic, which is a traditional binder that's used to allow it to get the pigment to the surface. That's the vehicle in older inks. Adhesives. I use two main adhesives. My students use one main adhesive. We use PVA, which is polyvinyl acetate. It's a glue which stays flexible and clear when it's dry, but which is perfect for book, right? Because you need everything to move. And methyl cellulose is just a weaker glue, but it's used a lot in book repair. And a lot of bookbinders will mix the two together. I'm kind of hardcore. I just go straight through the glue. And the difference between glue and paste, in case anyone asks you, is that paste can be undone. Glue is permanent. Once the glue sets, and it takes 12 hours to set, you're done. This is not coming unstuck if it's the appropriate, if you use it appropriately. And then I made that list in my head again. Okay, sticking things to other things. What can I use to stick them together? I have rivets, sewing, stapling, snaps, wheat paste, honey, egg white tape, burnishing, nailing, gum, which is disgusting, but it works. Brads, clips, resin, with popular resin around here is E6000. You can get it at your local hardware store. Bezels, so if you remember, if you arc metal around something, it also holds it together. Rabbit skin glue, wax, weaving, and folding. So the book on the left, which is called Nocturne, it's a Jacob letter. It's a toy that's been made into a book. And some of the materials in that book, like that eye up in the front, that's a peach pit pad. Because I like to see how I can integrate natural and found materials into my work and repurpose it. Other things in that book are star anise, ashes, cherry stems. This is sounding like a nightmare for you, isn't it? And you see on the bottom right deer teeth, which are serving as metaphorical mile markers. But so that's what I'm saying. I don't think about the longevity. I think about what I want to say and what material do I want to do that voice. And the seeds on the top right actually come from a friend's stress ball that exploded. And I don't even know what kind of seeds they are, but they're so beautiful I had to use them. I work with glasses on. Yeah, I'm not sure. They're like somewhere, they're like really flat quinoa. So you just take quinoa and make it grow flat. It looks like that. But I wear magnifiers to work. And so one of my goals is to get to a point where you can see what I'm seeing when I make it. Because each seed has a voice. Each plant is unique. Each seed is unique. It's really one of my favorite parts about working with this stuff. Poppy seeds are extraordinary. The variety of value and color is unbelievable. But unless you're in the dark now, you put your glasses on, you have to see what you need though. So I've always been encouraged and concerned with using materials that will last. But I've always prioritized my conceptual material concerns over the archival aspect. When you see the bird on the left, what I did is I went to the gallery here, the Gray Gallery, and I asked Susan for all the humidity charts and just wove them together because that's what I wanted the bird to consist of. So it's sort of a tongue-in-cheek nod to a concern with atmospheric and material conditions. And then the page on the right, there's just some playtime from the journal. I think playtime is essential. So the real question is, nothing lasts. Is it archival? My students are always like, well, why can't I use duct tape? Well, you can use duct tape, but I'd rather you didn't. And because as an artist, I believe that I have a number of responsibilities that lie beyond the stereotypes. So that wacky artist and societal expectations, and one of those is toward the individuals and collections who purchase my work. There is an expectation, which I'm happy to meet, of high craft and high quality of materials. And even if I use items I found on the street, I do address the places on that object that are required to be cleaned for materials. When I was in Brooklyn the last time, I found all these really great pink film circles with metal on the outside, and then so I collected a lot of them. Somebody told me they're the inside lid to crack files, which is really disappointing. And I have no idea how clean because they don't want to touch them. I'm so grossed out. But they're perfect. And I was thinking, oh, I found all these rose-colored glasses. This is the perfect metaphor. So one day I'll figure it out. Maybe we'll have a little conversation over nice glasses or something. The question is, are you going to make a cake with Scharfenberger, or are you going to make it with Hershey's chocolate? It's a question of quality. Yes, the recipe works both ways, but why wouldn't you use good materials? Why wouldn't you use high quality ingredients? It demonstrates a respect for the craft, and it's an understanding for the voice of the material. If you want chocolate, you want good chocolate. There's an appropriate time for every material and an appropriate way to use it. And in an appropriate way, and it depends on your intent. You should always use hot, right? It's a sign of maturity for you as an artist. There can be times when less than archival materials like duct tape are appropriate, like those crown dresses. But it's got to be conceptually based. You have to be able to justify and explain it. And it may be a question of material availability. If I live in a shanty town, I don't have access to Scharfenbergers. The fact is, if I have chocolate at all, I'm lucky. So I'm going to make it my art out of what's around me. And in that way, it is very much a historical document of who I am and the time I live in. Again, I don't think about this when I'm setting up. I set out to just make my piece. But I think viewed in a larger context, we do have responsibility. So you can MacGyver your way for anything. We're pretty excellent. And it's pretty fun to do that. Can I make this material do that? But the sensibility of material choice combined with things to the highest level of craft demonstrates thoughtful practice. And this is the mark, in my opinion, of a professional. It's that thoughtfulness. I care not because I have an ego-based desire for my material to live long past my existence. It's sort of irrelevant in some way to me. But it matters to me a lot that my artwork is respectful of the craft and the history of the craft. And the people who will be interacting with that artwork. And I feel very fortunate to be able to have that as an option. So thanks. I'll be next.
I'm going to talk a little bit about chemistry. And so I've picked two pieces I didn't spend a minute ago to show. Both were painted in the late 19th century. The first year I'm showing is Bank of the Seven. The second is a view of Arlesworth irises. And again, painted in the late 1800s. And as a chemist, what I'm very interested in, chemists are interested in, the materials and the compounds that make up the things that are around us. And so we may ask, what are the different materials that make up pigments in a painting? What are the materials that we're using to bind it to the canvas? I didn't show a frame here. I don't have any experience in frame selection. Although it's an excellent displays at a museum once. But what about the lacquer on the wood? All sorts of different materials that we're going to use so that the artist can create whatever they so desire. What I want to focus on here in particular is the yellow pigment, which I hope everybody can see. This is referred to as chrome yellow. And this became available more widely available to artists in the late 19th century. And it was sought after because it's a very, very intense color. So it offers new artistic possibilities. So the chemists, we want to understand what is the nature of these materials so that we can be inspired to make new materials that offer new possibilities to artists or whatever application that we may have in mind, but in this particular case it's art. And this particular pigment is widely used by other artists, so Paul Cézanne and George Seurat. One of the problems that was noted with it is that with time it would actually turn brown. So over time, painting would get a bit more brown, where there were these originally intense yellow colors. So the chemistry want to know what is the material there and what's happening to it. And the idea is maybe we can reformulate it so that when people choose this color in the future, it will be at least more stable. Or secondly, maybe there's even the possibility of halting the process or maybe even reversing it. Now, that's a question for a conservator, that we even want to do that, but it would be nice to have a possibility. So I'm going to focus in on now a little bit of chemistry. I'm not going to show many chemical slides, but the particular compound in question here is called chrome yellow. And it's the compound is actually lead chromate. It's a color of different elements, different colors here. Actually, John Kennedy's kind enough to do this for me, so that everybody can understand. I'm talking about PD is lead, CR is chromium, and then O is oxygen. And this, the particular formula here is telling us the discrete ratios of these elements combined. It's a single lead atom, a single chromium atom, and 4 oxygen atoms combined to make lead chromium. And depending on the source of the material and who processed it, you may find different formulations of this. So in some cases, the lead chromate is mixed with a little bit of lead sulfate, and then we have a sulfur atom in there and some more oxygen. And this particular mixture gives it a more orangish color. And we can also mix it with lead oxide, which gives it a little bit of a paler yellow color. So these are the formulas that we're talking about here. This is the question is what we'll address here in a little while, what's happening to the lead chromate over time. Now what I want to get into a little bit is how light interacts with matter. We're talking about visual arts here. So the light is shining on the painting and then our eyes are perceiving this light. So I want to turn quickly to a little bit about some atomic theory here and touch upon something that John Kenny was talking about earlier. We can find very, very simplistic model of the atom that's going to serve our purposes just right here. But we can really think of an atom as a very, very simple thing. A nucleus here, so a collection of some positive and neutral particles that are going to cluster together at the center here. And this is orbited by electrons. And chemists are very fascinated by the electrons because this is where a lot of the action is. And you can think of the electrons as circulating down these orbits. I've drawn this kind of a planetary type stream. If we want to be more quantitative, we would then look at quantum mechanics. And the picture gets a little bit funnier, so I don't want to kind of go down that avenue at this point in time. But we can think of this electron circulating around the nucleus in a particular orbit, and we can think of that as possessing a certain amount of energy. And if we shine some white light on it, just as John Kenny demonstrated with this light box, so we have some red, green, and blue light. If we shine light on it, these oscillating electric fields will interact with the electron because it's also a charged particle. And what we're going to be able to do, if we match the energy of the light, that wavelength, the wavelength has a particular energy associated with it, that matches a particular gap in the new orbit. The molecule of this atom is going to absorb that light. And what we're going to do is promote the electron to a higher orbit. And it's shown down below. This is after the light has been absorbed by the molecule. Now, I can't pick any particular orbit that it wants. This is not some sort of just infinite continuum. But these things are what we call quantized. So I'm going to take very discrete steps. When I walk up the steps to my building, I have to walk that one step on the next. It's not like a cartoon where I can take half steps and any funny fraction thereof. They're very, very discrete. So in this particular example, the amount of energy represented by that gap, I've chosen to match the amount of energy provided by a green light wave. So after that, the white light interacts with my molecule, the electrons are promoted, the green light is now missing. And so what's passing through the molecule here in my atom is the red and the blue light. And in particular ratios, I probably perceive this as a purple atom, in this particular case, a purple molecule. So the green light has been absorbed. Now, this is not just the end of the story here. This is just why we receive the color of this particular atom. But what we're interested in, we're going from what we may call the ground state here, the state that we just find the atom in, the conditions that we experience here. But in this particular case, we're going to call this an excited state atom. This can have more energy. And there are a bunch of interesting things it can do. One of the things it can do, the electron can pop back down to its original orbit. Now it has to give up that energy somehow. And one way to do that is re-emit a green wave, re-emit that light that it absorbed. So in this case, we call this either fluorescence or phosphorescence. This gets back to the ground state, but now the molecule is emitting light. And I'll show you some examples of that in a minute. Another thing to do, it's not as exciting, but you can actually pop back in here and give this energy off as heat to the surrounding atoms around it, the molecules that are around it. And here's an example of one of these emissions of light. This is phosphorescence in this case. And what I'm showing up top are 3 different molecules. And I don't want to focus too much on exactly the notation here, but what I hope, I want to treat this in more about a Sesame Street kind of manner, is that there are very, very subtle differences between what I'm showing up here. In particular, hopefully you'll notice that the ring at the bottom, maybe has 2 nitrogens in it, maybe it has none at the top. Here they pop back down again. So there are very subtle structural differences in these molecules, and when we shine ultraviolet light on them, they re-emit light in different colors. And so these materials, these are actually made by some graduate students here at ECU in the chemistry department. We've visited with Alex Garner and Chopin Hoseland. And they design molecules like this so that we can design things like display screens. So if we mix RG and D, red, blue, green in different portions, any type of color. So now we can use these types of molecules to fabricate devices that we're interested in. And as another demonstration, fluorescent molecules, very, very useful in medical research and chemical research, biological research. And as an example, I have a little vial here of a compound called calcium in aqueous solutions. So graduate students in my lab mixed this up for me a little bit earlier today. And if I shine a little bit of ultraviolet light, this is what we call a black lamp, so it's emitting ultraviolet light. You kind of see the glow in that particular case. So it's absorbing the ultraviolet light and re-emitting, it's emitting light at a slightly longer wavelength, one that we can now see, so that the solution appears to glow because it is re-emitting the light in all these different directions. That's just an example of fluorescence in this case. Now another thing that molecule can do is it can go on and actually react. We've now reconfigured the electrons in that molecule, and that gives it new properties. So this molecule can actually go on and react. And so as an example of that, I've chosen a biological example. So what I'm showing here are 2 structures. These are bases from our DNA. So thymine, so you know that there are people familiar with there are 4 different bases that make up our genetic code. This is would be represented by the letter T. And these molecules absorb light. They'll absorb light in the ultraviolet frequency range. So if I'm out sitting in the sun, I'm getting hit by ultraviolet light. My molecules are absorbing that. I feel some of that as heat. But we're going to reconfigure the electrons in these particular molecules. And in some cases, because the electrons have moved around, we've given these things new reactivities. And if there's a nearby thymine, quite often they can chemically bond with each other and make a new molecule. This is very stable. We're not going to unmake this molecule. So this now leads to mutations in our DNA, which may be cancer-causing, hence why I wear sunscreen when I go out, something that absorbs the UV light for me so that parts of my skin and my DNA are not absorbing that particular wavelength of light. It's the higher energy wavelength. Okay, now this is the probably the most chemical slide I'll put up from here on out. But I want to talk just a little bit more about electrons, that are just so important. So I'm showing a very, very simple molecule here. This is called ethene. It's a very, very simple organic molecule because it's carbon in it. The carbon is what people call an organic molecule. And I've drawn these lines between the atoms here. This is showing the connectivity here, configuration. So we're showing both the connectivity of the atoms and the geometry of this particular molecule. And I want to focus in on this little line here. What is this, a plastic stick, a wooden stick holding these things together? What the bonds are the sharing of electrons between atoms. To make another way to look at it, I've now represented the electrons that are being shared in dots. And we're going to notice that it's 2 electrons that make up a bond in each case. So electrons are the sharing, or bonds are the sharing of 2 electrons between atoms. And you notice there are actually 2 bonds between the carbons. So there are 2 bonds here. You can imagine that's a very, very strong connection between these 2 atoms. So it's going to be much harder to break potentially with carbon-hydrogen bonds. And these exist as pairs. So the pair, I want to focus on the nature that these things are pairs. Those pairs of electrons reside in an orbital. I'm going to represent this by a little line here. And the electrons by these little arrows. So there is a happy pair. And again, if we shine light on this, and what I don't look at the equation by hand, if I put a squiggly line here representing that, it exactly matches that energy gap. I can unpair those electrons. I can send one of them into some other orbit. And what I've done now, since I've reconfigured the electron configuration here, I now have unpaired electrons. This makes the molecule very, very unstable. We call these types of molecules radicals. You may have heard of reactive oxygen species. And what it's going to try to do is find itself a partner. And so when my molecule goes and bumps into some other molecule, it's probably going to try to strap an atom and get another electron to pair with. And so we're carrying out chemical reactions in this particular case, making new molecules that may have new properties. And this thing is now changed. So this particular starting compound is now disappearing. And now what I want to do is kind of turn back to the two paintings you're looking at. What I have here are some cross-sections of paint chips from those two paintings taken from areas where the chrome yellow is used. So we're doing a microscopic analysis here. This is just under a microscope, so very, very small pieces so that we're not destroying too much of this painting. This is a study carried out by researchers at the University of Antwerp in Belgium. And the idea is we're looking, if we were looking at the painting, our point of view would be like this. So we're looking at cross-section, and we're looking at the layers of pigment like strata in this particular case. You notice the surface is really darkened here, and then beneath we see the chrome yellow. So again, with the darkened surface and chrome yellow and beneath that, we see other pigments here. And so what we want to understand is what happened to the pigment up here, and why isn't it still like the pigment's a little bit deeper down? And we can do a chemical analysis on this. And the way we do that is we use light spectroscopy to study that. The interaction of the matter here with light reveals to us the chemical composition. And so I'll tell you some results about that in a minute. But in lab, we want to understand what are the factors that will lead to this type of darkening. And so what we can do is an experiment under more controlled conditions that will help us understand the particular pictures I've shown you. What I have on the top screen, I'll go over here. What I have on the top, on the top row here are some paint samples. And so the first paint samples are actually historic paint tubes. The first belonged to Gaulis von Reuters, but not Reuters. It's a Flemish painter. This paint sample is actually from the 1800s, been stored in a paint tube for this time. The two others have been stored at a museum in Belgium, and so these are from the late 1800s. Still, you can uncap them and smear them on glass plates here. And the last sample is a laboratory prepared sample. So it's 80% lead chromate, so that PD CR04 mixed with some linseed oil. That's the binder that makes the paper oil. And we want to understand what happens with the age. Now, we don't have 100 years to wait to see what's going to happen, so we're going to speed the process up. We suspect light is the key culprit here. So we're going to put this under a really intense UV light for about 800 hours. Come back later, and you're going to notice that, especially in this the first sample here, it's darkened considerably. The second sample, a little bit less so. The third sample is very, very slight darkening, and the lab prepared sample, very, very slight darkening. And again, we can ask them, we can chemically probe and say, what is the composition here, and what is the composition here? How has it changed? What is the chemistry going on? And the analysis, which I'll show you here, in what's going on in both the paintings and in all the paint samples here, is that the chrome yellow, PbCr04, is being converted into chromium oxide, Cr2O3. So this is the conversion here. These substances are different, so they have different colors. These are solid samples. We're showing something that's chrome yellow into viridian green, so you can understand that the intense yellow, the material giving rise to the intense yellow color is fading. A new color is coming in there, depending on what other pigments are around, that we could reasonably understand why the pictures are brown. And if we look chemistry-wise, again, we're really interested in electrons. I guess we're electron accountants. And what's happening is the chromium is going from a +6 oxidation state, very, very high oxidation state, to +3. So how do I get from +6 to +3? I add some electrons to it. So somewhere, this chromium is getting electrons, and the light is inducing the reaction. So we can think of the light as being the reactant in this case. Now you may ask where those electrons come from. They can't just magically appear. It appears to be the samples that have more sulfates in them are the source of that, and that is still a point of further investigation. And then we get a sense of what's going on. So one thing we can do is prepare the lead chromate in a different fashion to at least have less sulfates in it. Now, I don't know about any means of reversing this at this point or necessarily even halting it. That's a question for conservators. If we had that ability, what a conservator thing to do with it. And I guess at that point there, I'll conclude my statements here and pass this off to Suzanne Reed to tell us more about conservation art.
Thanks everybody for coming tonight. So I think we have learned tonight that art and science is really truly about attraction, and attraction is kind of where I come in with conserving individual pieces of art. So tonight I'm going to talk about kind of what conservators do and how it applies to maybe perhaps what you do as an artist or what you do as a scientist, and how we preserve that experience of attraction, how we preserve that artist intent. So we start with the first impression, and I think in any laws of attraction, you're kind of in the initial meeting phase of a relationship, and you want to make a great first impression. And the conservator essentially comes upon a work of art, and we try and get a good first impression from what the artist wanted us to see. This process is very personal in some cases for conservators, and you are actually taking apart the object when you're talking about historical materials and peeking inside of it and becoming very close with it in a sense. And I kind of want to know as a conservator what it's made out of. And I'm now looking past that aesthetic surface, past what the artist intended, into what the object is made out of. So that's a part of meeting the artwork and getting to know it closer before I actually start any kind of treatment or interpretation of the art. So how do I do this? Well, any kind of first impression is knowing who you are as well. And conservators essentially have a background in art history, in chemistry, and also in various studio arts. And there are several conservation programs in the United States, I shouldn't say several, there's two, University of Delaware, Buffalo, and New York University as well, where they all gain experience in various aspects of science and art in order to kind of create the ultimate conservator. So also, there's other people beyond objects conservators that deal with specific material types, that deal specifically with book and paper, or textiles or paintings. Objects kind of represent an entire three-dimensional world, which is quite intimidating sometimes. We do have to know a lot about every single material type that exists, essentially, every single material type that an artist is going to use. There's also sculpture, architecture, more recently electronic media conservators. Now we're having to preserve this digital art that not only the format that it comes in, but also the experience that it gives the viewer. And lastly is conservation scientists, which are gaining popularity. The next kind of step in this process is placing the object or the three-dimensional piece into a broader cultural context. And this essentially includes a geographical perspective of where the object came from. This can assist conservators essentially in determining the origin of the piece and determining the value system that's integrated into the object and predicting the kind of preservation issues, and I'll explain how that relates to this later. Next is the understanding that art is a non-renewable resource, that art has been created over thousands of years by humans as material culture, and understanding that much like our own natural resources, these cannot be renewed. Once an art piece is made by an artist, it's unique, and we need to preserve it as such. Lastly is our thought process that goes into these art pieces. I'm going to zoom back out because I wanted to explain this image here. This is a picture from South Africa. This is a pottery studio in the Lunga township. And this is an extremely impoverished area in South Africa, the township areas. This specific pottery studio gives locals the opportunity to come in and be creative and sell their artworks and create a little bit of a profit for the area. So that can be an important part of understanding the artwork and understanding what needs to be preserved. So I'm going to jump ahead. Sorry, don't get motion sick. So again, coming back to that thought process, and Lisa Beth touched on this a little bit, really understanding the object and what it's all about. I have very close relationships with objects because of this. Essentially, the first part is understanding the material it's made out of. When the artist chose that material, they're concerned with the cost, the availability of the material, and the properties, the working properties of that material. So for instance, I can extrapolate that if somebody didn't have access to a certain type of material, then most likely didn't use it in their artwork, or quite the opposite, that they would have used it more commonly in their artwork. The second is the artist, what their skill level is, what their knowledge of the processes are, their knowledge of the material types are, also what the function of the object was supposed to be, and also the aesthetics. What kind of visual stimulation is the object supposed to impart in the viewer? This all creates an object, and I've been using the terms object and artwork interchangeably, but I refer to any kind of three-dimensional piece that is tangible, is concrete, I can touch it and handle it, versus other types of intangible artworks which are also preservable. You might be talking about poems, dance, songs, and so on. So I deal specifically with things that can be three-dimensional. The major critical part to understanding an object is to evaluate the life cycle that an object goes through. And we call this the use life. And the use life is essentially the entire life that the artifact has gone through, which ends at these last stages: storage, recycling, reuse, discard, or loss. Essentially, the object reaches one of those stages after it's gone through this period of use. The conservator comes into contact with the artwork of the object through either sale to a museum or to a private individual, recovery through a burial process and archaeological excavation, or through this very complex gift exchange process that we have in many societies. So essentially, that's when the conservator is most interested in studying, is the use life, how the object is actually used, or the artwork in this case. Next would actually be examining and interpreting the object. This is essentially, again, one of the most scientific processes that conservators use. Really, the first part of this is understanding the materials and what they're made out of. Understanding what the material is composed of. Is the original artist's material going to be compatible with archival products that I use or conservation products? How is that material going to interact with the treatment overall, with the solvents I use to clean it, or with the adhesives I use to repair it? What's the long-term aging properties, not only of the archival products that I use, but also of what the artist uses? I know a lot of artists like to use chocolate and food, and those are really difficult for conservators. But also, lastly, is what, sorry, my sentence got cut off, but what analytical techniques are going to help me understand the work? And this is where my relationship with John and Colin come in. The scientific analysis. So you're kind of getting the understanding that conservators have to wear many hats. The first part of scientific analysis includes ultraviolet light. And Dr. Henny already pointed out some really critical concepts of light that are important for us to understand, not only as conservators, also as artists. So ultraviolet light in this case, this is a portrait of Queen Elizabeth I. And she belongs to the Elizabethan Gardens in Roanoke, North Carolina. And she was brought here so that we could study her and essentially provide some sort of sense of authenticity. So the Queen was very vain. She was known to be kind of destroy paintings that depicted her as an older woman. And obviously she's quite aged in this one. So this is a rare example of Queen Elizabeth in a portrait. The ultraviolet light, how this is important for me, is that I can use this type of light source to excite the paint molecules and actually show where there's areas of damage on the varnish. It can also show me where there's restorations, perhaps showing where something has been incorrectly restored or just even previous restorations. So natural products, for instance, some types of varnish, actually show up as like a mustardy deep yellow. Whereas we have modern synthetic products that show up as a bright white, just like your white shirt does under a black light. So ultraviolet is an extremely useful tool. Another example of this is this summer we spent in Israel researching Bronze Age bathtub features, just how it sounds, they're clay bathtubs. In order to know where to sample from these bathtubs, we used an ultraviolet light to see where there may be any type of organic residue. Specifically, we were looking for a technological manufacturing process. So light is extremely important. The second type of light that I use regularly is infrared light. Infrared light, again, as Dr. Kenny pointed out, we can actually see through the top of the painting onto the undersketch. The undersketch in many cases is made out of charcoal or other types of graphite. And that's important because it allows us to interpret the art, how the artist originally kind of changed it, moved the figures around, made it politically correct as it kind of aged through this decades or centuries. And it also can tell us where there may be areas of very thin paint. So for instance, where it may have been removed or just where it's come off over the years. Infrared also works as an analytical technique using Fourier transformed infrared. It's a big term and it's funny spectra, but essentially it produces this spectra that can tell us exactly what type of organic materials exist in the painting. And this is important for the reason that both Colin and Lisa Beth brought up about having those binding agents, linseed oil, or even egg in some cases. And that's important for me to know because I need to know if my solvents that I'm cleaning the painting with are going to dissolve that. The next type is microscopy. So this is perhaps the most critical tool for conservators. This particular painting was actually painted on a wood panel, 2 wood panels that had been splinted together. And we believe that it is a contemporary painting from 1545. The wood is consistent with that time period. Microscopy, particularly scanning electron microscopy, which is a really high-powered electron beam, allows us to see the individual wood cells. That can tell us where the wood is from, what time of year it was cut, potentially contribute to determining the age, but it can also tell us exactly what's causing deterioration to that wood panel. So in this case, we can see a very weakened wood cellular structure. This is not actually from the painting. We did not sample the painting at all. That was a very non-invasive analysis, but it does allow us to do that. The second type of microscopy we use, again with scanning electron microscopy, is pigment analysis, looking at those paint layers. And as Colin pointed out, we take a very microscopic sample that you would never see as a viewer from the painting. In many cases, it's a piece that's already fallen off, just from transportation or something. And we place it under the scanning electron microscope. In this image, we can see this is actually a paint sample from a maritime figurehead that we looked at in Namibia over the summer. We wanted to determine if the figurehead off of the African shipping coast there was American or Dutch. And so we sampled some of the paint that was on it to determine possibly where the pigments were made, where they came from. So this is a blue pigment here. You can see this is our bottommost layer. So it's sort of been attached to the wood. And then several times it was painted with this blue or dark blue color. And on the top, it was very popular for them to paint figureheads completely in white at one point. So based on this and in conjunction with other analysis, we determined that it potentially was of American origin. And that could have a huge impact on the history of Americans being in the African coast and whaling. On the right is actually the scanning electron image of that same paint sample. And you can see those brighter areas. Those brighter areas represent heavier elements. And again, that can help us, we can do analysis to determine exactly what elements are present. And again, as Colin had said, certain elements became present in the paint samples through several centuries and decades. So we can kind of pinpoint the time period for this as well, based on one little paint speck. Isn't that fascinating? I think it's amazing. Lastly is fluorescence. And John had brought up this idea of fluorescence. So we use essentially a process called X-ray fluorescence to determine exactly the elemental analysis of these. X-ray fluorescence can be used in conjunction with microscopy, but essentially you analyze the pigments and it gives you an elemental signature. And again, kind of looking at those individual elements can tell you where the paint came from and potentially what time it started to be used. Moving on to preservation, the most important part, right? So this is the picture of the queen was actually a picture of an X-ray fluorescent gun. It's, again, a non-invasive process. You don't actually have to sample the painting. You can do the elemental analysis just by holding it up to the painting. In this picture, this is actually a Civil War booth. So when I say that I don't just do artworks, I definitely cover the whole gamut. This is a leather boot from the USS Monitor. And it is in a waterlogged state, which presents unique challenges on its own. You can have issues with corrosion products, salts, bacteria, other types of organics in the water that can affect the object in a tremendously complex process. I did want to point out that there are a tremendous amount of decisions that go into treating an artwork. So using that analysis to understand the material better, using that cultural context to understand where it came from and why the artist and how the artist made it, is all done for the treatment, to understand exactly what kind of treatment you're going to use. So this decision-making process is quite complex. Realistically, conservators can only use what resources they have. The first are financial resources, exactly what kind of monetary resources you have through your institution or through the client. The second is material resources. When I worked with the Antarctic Heritage Trust that was based out of New Zealand, we were working on the early explorers' huts based in Antarctica. And we were extremely limited in what kind of materials, what kind of chemicals we could bring in. And so I had to get used to working with non-traditional techniques and an accelerated working pace. So material resources are incredibly important. You always think that you can just order it from the catalog as a conservator, order that archival product. But that's not always true, as I learned. Also, what condition is the object in? Seems like a pretty straightforward question, but actually asking how structurally stable is the object? Is it actually going to be able to withstand its own weight, its own structure? In some cases, you may have marble sculptures where the legs have broken off in natural disasters or so on. And you may have to install dowels or iron rods inside of them or titanium rods. How do those rods affect the object later on? Are those going to fail and cause further structural damage? Will the outcome of the treatment actually affect the condition of the artifact? Is it going to make the artifact worse? Every conservator's nightmare, right? Your treatment doesn't turn out as expected. And is it even possible to perform a treatment on the object? In some cases, your artifact may be so deteriorated you can't actually perform an invasive treatment. In that situation, you would use a process called preventative conservation, which is more controlling the environment around the artifact, rather than performing a remedial treatment on it. Moving on to ethics, I felt like this was a really important point for me to bring up to you tonight. Conservators are not governed by any kind of laws or regulations necessarily. We're really held accountable to our own peer groups, to other conservators. So therefore, we signed this code of ethics that is kind of represented by our professional society, the American Institute for Conservation. And these are listed here, but essentially, the biggest issue with us is reversibility. The materials we use have to be able to be undone, so that in the future, when better materials are developed and that technology is around, they can undo what we did. It's funny because we're looking at the treatments that were done 20 years ago and thinking, why did they ever do that? And they're going to do the same thing with our treatments because they didn't have the knowledge of what we have now. You can see there's some more general ethical codes here and more specific ones. But essentially, you also need to be able to create and maintain documents, create the paper trail for your artifacts so somebody did know how you treat it, to know what materials you added, not just the artist, but what you added to it. Perhaps the largest part of this process is understanding the artist, and that is part of that decision making when you're talking about a treatment. Understanding the artistic intent versus the preservation. In many cases, these are in direct conflict with each other. I talked about that chocolate sculpture. And in some cases, the artist does want the material to deteriorate. A lot of our indigenous cultures, Native Americans, the Maori of New Zealand, they believe that there's a spirit in objects that they create, that they're actually emotional beings, that they're people, essentially. And so they feel that they need to go, those objects need to go through this life cycle and be allowed to deteriorate, be allowed to die. So you're taking that away from the art piece if you're trying to preserve that. But then again, it becomes part of our larger cultural heritage. Part of our cultural heritage as a society, not just as that individual culture. So talking about whether you're preserving the cultural record versus the cultural heritage, are you preserving the object because it's unique to one society, or are you preserving it to the greater population of humankind? It all comes down to preserving the intention of the artwork. So Colin had suggested, put me on pressure, what do conservators do, and what do we need to put paint back on? How do we preserve it? Do we keep it that yellow mustard brown, or do we actually add the color that the artist originally intended? You know, we now have the technology to understand what the artist's intention was. We didn't have that before. So do we actually paint over and allow us to kind of experience those vibrant yellows again, or not? That's a very strong question. So the last and final thing is, of course, how our training and experience dictates what we do. This seems self-explanatory, but we generally call in other specialists. So for instance, I wouldn't feel comfortable treating a painting like that. I would probably call in a specialist, paintings conservator. So you have to know your limits, especially as a conservator, because you don't want to damage the object or the artwork further. One other kind of last major decision-making or effect on how we treat objects is our priorities. So in many cases, you can have institutional priorities, you can have the artist's priorities, and you can have the conservator's priorities, and these can all be, again, in direct conflict with each other. So the only way to make it work is to compromise. Institutional priorities. Again, They are, again, preserving things in perpetuity. Their whole concept is to collect and to show and to allow for research. But they also need to make money. So they need to have exhibitions, they need to have programs. But those things are not always healthy for the object. You don't always want a piece of artwork on display for years at a time, especially under certain lighting conditions. So those kind of priorities for the institution could be in conflict with the preservation. The artist has their priorities. They want their art piece to be displayed a certain way, perhaps for a certain amount of time. And again, that may be in conflict with the preservation of it. And then of course conservators, everybody says that conservators want to preserve things in a dark, cold room, and it's absolutely true. But I think, I think we have to compromise, and we're now understanding that. So those priorities really have a huge effect on how we treat things. So I didn't really want to get too much into how we specifically treat objects, but I did want to mention some of the things that affect how a conservator thinks about treating materials. And so all these kind of processes bring us back to that original goal of having that first impression. And in a way, I felt like conservators take on the role of the artist because we are trying to give that back to the viewer. And somebody, during one of our discussions when we were brainstorming for this, was that conservation is an art form, and I never, ever thought of that before. Because in some cases, I do detach myself from the artwork. But in other cases, I do become a part of the artwork. I do feel some sense of loss when I've worked on an object for hundreds, thousands of hours in some cases, cleaning every little nook and cranny. And then when I have to give that back to the client, I feel a little bit of loss. So it works both ways, I think. And I just wanted to kind of end that saying science is really critical in this entire process. And it does assist conservators in making those decisions on how to treat an artwork. It's not just art, it's not just politics. Science has a big role in that. And it's cool, you know. But it helps us achieve that overall goal of preservation that we want with the artist. So thank you very much. So, sorry. So you were talking about your adhesives, and that really triggered something. The adhesives that we use are considered archival in that they have good gauging properties. If you outlast you, they say at your institution, and you're good to go. But we like to think 50 or 100 years is kind of our archival thing. But you had said that once you use an adhesive, it's stuck there forever. And we'd like to think that. But we know that in 100 years, 500 years, that's not true. Do you think that would affect what adhesives you choose? Or
Yes.
Yeah.
Everything will come unstuck my hair, or will just drop and all those seeds will go to the bottom.
Yes, exactly. That's a nightmare knowing where to place those seeds again.
I'm still going to use the same glue. You know, there are glues that you don't use. You don't use Elmer's glue. It turns yellow and crusty and falls out. Yes, tastes sucks. You should say no to yes. But PVA, I feel pretty confident about its potential longevity, and I don't think of my artwork as being passed down. I think of it as something to be experienced and engaged with, and maybe hopefully stimulate someone in some way to do something that they might not have done before. Think about something that they haven't thought about before, or just have a good time. So as long as they're having a good time and it's long enough of a good time, and the institution that purchased it feels that their investment was enough of one that they got the value out of it that they spent, I'm okay with that.
I just thought it was really interesting that you described it in such beautiful detail about how you enjoyed every individual seed.
I love
And
it.
how could I recreate that as a conservator? Like, you had placed it there specifically for that reason. I would be able to recreate that process, which is unnerving to me. I could apply that for your artwork. Yeah.
And that's something actually for the students that's really hard. Okay, so you give me a book and it's falling apart before it crits over. We have a problem, we have a big problem, because that wasn't your intent, or it wasn't what you made it. So there are books that are made to vanish, there are books that are made to fall apart, but most of the time that's not your intent. You're trying to communicate or convey an idea. And so for me, the way the light's working in materials, these are things that I'll think about more than you know, is this going to last 150 years? It'll last. The oak gall, I was reading about it because I thought it was a quick process. Some of the documents in the piece of music inked up and fingerprinted with oak gall lasts 1,000 years. That's enough. More than enough. But would you, your cultural artifacts are very old, and look how much we get from them. I mean, I will think about it. I don't have a better alternative right now that I can afford.
Maybe if you're concerned about your own type of art, is there a type of degradation process that you're already seeing in the art you make? Metals, ceramics, painting.
I have a different sort of question. What's the lifetime, or what's the length of fluorescent pigment's life? How long would fluorescent pigment be able to receive and release?
Depends on the material. I think that could be totally material dependent. I mean, some of them are quite stable. A lot of fluorescent molecules that are fluorescent that I have on my chemical shelf. Usually just to preserve them longer, I'll make sure that they're sealed in dark bottles. Some of them that are a little less stable, I'll store in a deep freezer. So it really depends on the molecule.
What led to that was we actually had a retrospective for one of the only artists who works in glow-in-the-dark painting. And it was quite interesting. I always wondered how long that would actually last. They were quite interesting.
Certain colors may fade faster than others, so I can't answer specifically. We'd have to know exactly which one we're talking about. And a lot of times just by looking at the molecule, I can tell that and I'll do some experiment and find out how long will it last.
Does that have to do with entropy?
The universe doesn't do that. How reactive the product is and what we mean by the sex. Thank you all very much. Appreciate it.